Structure of AX2 type. Structure of AX2 type compounds. Structure of AX2 type compounds. Structure of AX2 type compounds. Okay. Then the two most common structure are fluoride CIF2 and rutile TiO2 in AX2 type compounds. First is calcium fluoride. Calcium fluoride. Calcium fluoride, okay? Calcium fluoride structure. In calcium fluoride, calcium fluoride. In calcium fluoride, the radius ratio value is 0.73. Radius ratio value is 0.73. On the basis of radius ratio value, its structure should be body-centered cubic arrangement. Structure is BCC, body-centered cubic arrangement. In fluoride, each calcium ion is surrounded by fluorine ions. As fluorine ions are double as calcium ions. Okay. In fluoride, calcium ions is surrounded by 8 fluorine ions. Calcium ion is surrounded by 8 fluorine ions. 8 fluorine ions. As fluorine ions are double as calcium positive ions. Okay. The coordination number of both ions is different. 4 calcium positive ions are tetrahedrally arrangement around each fluorine ions. Thus the coordination number 8 and 4. Then the coordination number 8 and 4. Okay? 8 and 4. This is an example of 8:4 arrangement. This is an example of 8:4 arrangement. Calcium positive ions in fluoride structure arranged in the face-centered cubic closed pack CCP. Okay. Thus, coordination number of 8:4 arrangement. Calcium positive ions in fluoride structure arrangement in face-centered cubic closed packed type of arrangement. All type of 8 octahedral sites created by 4 calcium positive ions are occupied by 8 fluorine ion. Calcium fluoride structure has been used to show also this figure. Okay. The other compounds showing this type of structure are barium chloride, BaCl2, BaF2, SrF2, CdF2, HgF2, and PbF2. Okay. Next is titanium dioxide. Titanium dioxide, TiO2, titanium dioxide, okay, rutile structure, okay. The rutile structure is found in many crystals where the radius ratio between 0.414 to 0.732. Okay. The radius ratio value reveals that one ion has coordination number 6. So from the formula of TiO2 titanium oxide, titanium dioxide, it follows that the coordination number other ion must be 3. Coordination number other ion must be 3. Hence titanium oxide has 6:3 type of structure. 6:3 type of structure. 6:3 type of structures, and each titanium ions is octahedrally surrounded by octahedrally surrounded by 6 oxygen negative ions, and each negative ion is ion has three titanium positive 4 ions round it in a plain triangular arrangement. The structure of titanium oxide has been shown. You can show this structures, and the structure of calcium chloride, CdI2 are also 6:3 type structure. Okay, structure. Okay. Then example. As an example, a solid AB has sodium chloride type structure. If the radius ratio of cations is 100 pm, then calculate the radius of n ions. Okay, since AB has sodium chloride type structure and the coordination number of A positive ions and B negative ions are 6, so A positive ions occupy octahedrally holes for fluorine of octahedrally holes. The value of radius ratio R positive ions upon R negative ions should be between 0.414 to 0.732. Radius ratio in ions. Radius ratio in ion is R negative ion is R positive ion upon 0.414 to R positive ions upon 0.732. Then this is 100 upon 0.414 to 100 upon 0.732. 100 upon 0.732, and this is also converted into 1.6 to 136.6 pm. Okay. Hence the radius of an ion B negative ions will be between 136.6 to 241.6. Okay. If the radii of sodium positive ions is 95 pm and chlorine is 181 pm, what is the coordination number of the both ions? How is the crystal structure of sodium chloride? Okay. Then according to questions, our sodium ion is 95 pm and radius of chlorine ion is 181 pm. According to questions. Okay. Then R Na positive ions upon R Cl negative ions. R Cl negative ions is 95 upon 181, that is 0.525. Since the radius ratio value is less than 0.732 but greater than 0.414, hence the cation will be occupy octahedral holes. So the coordination number of both the ions is equal to 6. Coordination number of both ions is equal to 6. Sodium chloride has a face-centered cubic arrangement. Face-centered cubic arrangement in which sodium positive ions occupy the octahedral source. Okay, thank you. Lattice are crystal defects. Lattice are crystal defects. An ideal crystal is that which has similar unit cell containing the same lattice point throughout the whole crystal. At absolute zero, most of the crystals have well-ordered arrangements of ions. In such crystals, there are no defects above absolute temperature. Deviation takes place in a regular arrangement of ions in crystal. This constitutes defects in crystal point. Defects is most important defect among the different defects which are found in crystals. The crystals found in nature are prepared in the laboratory contains imperfecting in the formation of crystal lattice. The defect produced a great effect on physical and chemical property of solid. Point defects. Which defects? Point defects. Point defect. The defect which belongs to lattice sites. The defect which belongs to lattice sites or points are known as point defects. The defect which belongs the defect which belongs to lattice sites lattice sites are point lattice sites are point are known as point defect are known as point defects. This type of defects arise due to displacement of cations or anions. This type of defects arise due to displacement of cations. Displacement of cations or anions from their appropriate sites. Appropriate sites are points. Appropriate sites are points. These are of following types. First is stoichiometry defects. Stoichiometric defects. Second, non-stoichiometric defects. Non-stoichiometric defects. Non-stoichiometric defects. Second is non-stoichiometric defect, and third is impurity defects. Impurity defects. First stoichiometric defect, second non-stoichiometric defect, and third is impurity defects. Okay. First point, stoichiometric defects. Stoichiometric compounds are those where the number of the different types of atoms or ions present are exactly in the same ratio indicated by their chemical formula. They obey the law of constant composition. Those defects in which stoichiometric are in the ratio of cations and anions do not change are called stoichiometric defects. Two types of defect may be observed in stoichiometric defect: Schottky defect, Schottky defect, okay, Schottky defects and Frankel defects, Schottky defects and Frankel defects, okay. Stoichiometric defects, stoichiometric compounds Stoichiometric compounds are those where the number of the different where the number of the different are those where the number of the different types of atoms, different types of atoms are ions present are exactly in the same ratio, exactly in the same ratios indicated by their chemical formula. Their chemical formula, okay. Stoichiometric compounds are those where the number of the different types of atoms or ions present are exactly in the same ratios indicated by their chemical formula. They obey the law of constant composition. They obey the law of constant composition. Those defects in which the stoichiometric are in the ratios of cations and anions do not change are called stoichiometric. Those defects in which stoichiometric are in the ratios of cations and anions do not change are called stoichiometric. Two types of defect may be observed in stoichiometric. First is Schottky defects, and second is Frankel defect. Second is Frankel defects. Second is Frankel defects. Okay. First is Schottky defect and second is Frankel defects. Okay. Schottky defect. What is Schottky defect? This type of defect arises when same number of cations and anions unoccupy the lattice point and form holes. It consists of a pair of holes in the crystal lattice. One positive ions and one negative ions are absent. You can show this type of defect. This type of defect arises when same number of cations when same number of cations and anions when same number of cations and anions occupy the lattice points and form holes. Lattice point and form hole. Lattice point and form holes. It consists of a pair of holes. It consists of a pair of holes in the crystal lattice. Okay, one positive ions and one negative ions are absent. One positive ions and one negative ions one positive ions and one negative ions are absent. Okay, and this type of defects occurs mainly in highly ionic compounds, and this type of defects occurs mainly in highly ionic compounds where the positive and negative ions are of similar size. Positive and negative ions are similar size. The crystal remain neutral. The crystal remain neutral because the number of missing positive positive and negative ions are same, and negative ions are same. Okay, generally crystals having 6 or 8 coordination number. Generally crystal having 6 or 8 coordination number is that highly ionic are examples of ionic solids in which Schottky defects arises from. Example: sodium chloride, CaCl, calcium chloride, and potassium chloride and potassium bromide, KBr. Okay, one defect is found in 10 to the power 15 lattice site. One defect is found in 10 to the power 15 lattice sites of sodium chloride at normal temperature. By increasing temperature, number of defects increase, and one defect occurs in 10 to the power 6 sites at 775 Kelvin and one defect is found in 10 to the power 4 site at 1075 Kelvin. Density of crystal decreases by increasing Schottky defects. Okay, one defect is found. Defects is found in 10 to the power 15 lattice site. 10 to the power 15 lattice sites of sodium chloride at normal temperature. At sodium chloride sites of sodium chloride at NTP, normal temperature. NT, okay, normal temperature. Okay, by increasing temperature, by increasing temperature, number of defect increases. Number of defect increases. One defect appears in 10 to the power 6 site at one defect appears in 10 to the power 6 sites. 10 to the power 6 sites at 775 Kelvin, and one defect is found in 10 to the power 4 sites, and one defect appears in 10 to the power 4 sites at 1075 Kelvin. Density of crystal decreases, and density of crystal decreases by increasing Schottky defect. By increasing Schottky defects. Okay, Schottky defects. This type of defect arises when the same number of cations and anions unoccupy the lattice point and form holes. It consists of pairs of holes in the crystal lattice. One positive ions and one negative ions are absent, which is shown. This type of defects occurs mainly in highly ionic compounds, where the positive and negative ions are of similar size. The crystal remains neutral because the number of missing positive and negative ions are same. Generally, crystals having 6 or 8 coordination numbers. Highly ionic are examples of ionic solids in which Schottky defect arises. For example, sodium chloride, CaCl, potassium chloride, potassium bromide. One defect is found in 10 to the power 15 lattice sites of sodium chloride at normal temperature. By increasing temperature, the number of defects increases. One defect appears in 10 to the power 6 sites at 775 Kelvin, and one defect is found in 10 to the power 4 sites at 1075 Kelvin. Density of crystal decreases by increasing Schottky defect. Okay. Next, Frankel defect. What is Frankel defect? We will be studying about Frankel defect and knowing about Frankel defect. Okay. Thank you.